Okay, as promised, just finish up this last little example of it's kind of a mixture between polar and cylindrical coordinates and relative motion, right? So, like I said, like we talked about in class today, we're after the velocity of B is seen from A. So what if I'm at A and I'm looking back at B? What does the velocity look like it's doing? And then I'm at same thing for acceleration. If I'm at A, acceleration of B is seen from A. So if I'm looking back at it like this, right? And so would the acceleration look like there? And then again, these bars usually refer to the magnitude of it. Okay, so you take the square root of the sum of squares of the vectors. All right, they're given to us is VA is 36, VB is 45 feet per second, and at the instant that's shown, they have an angle of 25 degrees in between them. The radius of A is 1250 and radius of B is 1200. And then the way we're going to get these accelerations and the velocities are as such. We just take this equation that we derived for the velocity of B. So it's going to be the velocity of A plus the velocity of B as seen from A. And if we're after this term right here, we just kind of throw that over there, and you get this equation right here. So that's what we're going to do. We need to figure out what the velocity of B is and the velocity of A, and then the acceleration of B and the acceleration of A. And then you subtract one A from B, and it'll tell you that relative velocity and relative acceleration. The thing that's kind of interesting about that, and I mentioned this in class, is you got to be careful of the fact that the ER and E theta for B is not the same ER and E theta for A, right? They're pointed in different directions. And so, you can kind of just based off of geometry, like, oh, if I know what this thing is doing this direction, I know what that's doing that direction, I can figure out what component of this is that direction, what component's that direction, and then what component's that direction, what component's that direction, and then compare them to these, which are lined up with the Cartesian coordinates, right? You could kind of do that just by looking at it and doing some geometry, or we can use those transformation equations that we had before, we kind of derived previously or wrote down previously. Okay. So we were right in the middle of this. We said, all right, let's look at car A. It's easiest to do this one in polar coordinates or normal tangent coordinates. Either one works, because it's traveling around in a circle. You can use either one. I chose to do polar coordinates for whatever reason. That's what I did. And so we're going to define the velocity acceleration in terms of polar coordinates and then transform them into the other coordinate system. Okay, so velocity of A, that could be written as R times omega in the E theta direction. We've seen this a lot of times. It's either R times omega or the velocity in the E theta direction, right? And either one of these things, R times omega is VA, and so it all works out. In this particular case, they give us VA. It says it's 36 feet per second, so VA is just going to be 36 feet per second, and I probably should be careful here and write this in the E theta direction as such, okay? Feet per second. A little bit more room here. Move that over a little bit. Okay, so that's what that is. Acceleration at A, right? This is the equation you would use for that. It's R alpha minus R omega squared. Again, this is tangential acceleration. This could also just be, AT, right? Or in normal tangent, it was just the acceleration of that, right? Or in this case, just like R omega was the velocity, the acceleration of the vehicle in the E theta direction would work. In this case, it says it's traveling at a constant speed. So then if it's at a constant speed, that means that there is no acceleration around that circle. There is no acceleration in this direction for either one of these things. And so that alpha term would be equal to 0, or the tangential acceleration would be equal to 0. And all you're left with is R omega squared in the ER direction. Again, you can write this two different ways. This could be R omega squared, or it could be the velocity of A squared divided by the radius, right? Either one of those works. And it's all just based off of this. R times omega gives us the velocity. And so you can imagine just doing some substitutions in the equation down below. So either one works. So the the acceleration is just going to be a centripetal acceleration. This is a centripetal acceleration component, no tangential. And, right, so we just substitute in 36 right there. So it's negative 36 squared over 1250. I don't know if I ever mentioned this before. I don't think I ever calculate that. I put it in my calculator later. Okay, so let's just leave it at that right now. Right? Obviously, you could write down a number for this if you wanted to. Okay, so that is car A, right? So now let's look at car B. Car car B. Right? Again, we're going to do this thing in polar coordinates to start out. Right? It is something that's traveling around in a circle. And so the velocity of car B is just going to be VB in the E theta direction. Right? And they give that to us. VB is 45 in the E theta direction. Right? And that is in feet per second squared. Feet per second. Okay. Same thing with acceleration. Acceleration of B. Technically, there's an R alpha term, R alpha in the E theta direction. Again, this is just going to be 0 because there is no acceleration of that car. Minus VB squared all over RB. So this is going to be negative 45 squared, and then RB is 1200. This will be feet per second squared. Okay, so that's the velocity of B, the velocity of A. That guy. And so everything underlined is what we need, right? So what I'm going to do now is I'd like to do this, right? I would just like to use one of these equations, right, for the velocity and this one for acceleration. But you can't do it because at this point right now, you're going to be tempted. You're like, well, this is 36 in the E theta, and this is 45 in the E theta. So I'm just going to take 45 E theta minus 36 E theta. Great, nailed it. The problem is the E thetas don't line up. Over here, right, this E theta is pointed this way, this E theta is pointed this way. You can't do that. So you have to get them in the same coordinate system. So we're going to get this thing into Cartesian coordinate systems, okay? And so I'm going to do that kind of the next step here. Okay. Cartesian coordinate system, everybody's favorite coordinate system. All right, and so I'm going to transform VA into that. VA is equal to 36 in the E theta direction. Right? And what I'm going to do, I'm going to cheat. I'm going to go up here, and I'm going to grab somewhere in here. I provide those transformations. One more of these guys right here. One more. So I'm going to use this guy right here. And the way you use these transformations right here, like I said, you could just look at the geometry and work it out yourself, or you could use the substitution, and that's what I'm going to do. I'm just going to take everywhere that you see an E theta, I just put this. That goes right there. All right, so this becomes 36 times negative sine 25. That angle's 25. That's in degrees, so you gotta be careful. Make sure you're doing these things in the radians or degrees. In this case, I'm doing it in degrees. So in my calculator, when I calculate sine 25, make sure you're doing it in degrees. Careful of that. That's in the I direction, plus cosine 25 in the J direction. Right? So that kind of transforms it into the Cartesian coordinate. VB, quite a bit easier, right? You could do the same thing. I could take this, right? And I could substitute, I could substitute it in there for the E theta direction, or I could just look up here and say, oh, would you look at this, right? This one's pretty straightforward. The velocity of B is in the E theta direction, which is this way, which happens to line up with the y-axis. So it's just going to be all in the J direction. If you put in that angle, the angle being 0 in that case, you put an angle 0 into this equation right here, you end up with the same thing, right? Or you could just by observation see like, oh, look, all the velocity is going to be in the J direction. So VB is just going to be 45 in the J direction. Right? There's that. There's that. Okay, I'm going to keep going. I'm going to transform the accelerations into the Cartesian coordinates now. You could calculate the velocities at this point, but we're going to go with this right now. Acceleration A. We have that before it. Acceleration A in the ER direction. It's going to be negative 36 squared divided by 1250. And the direction. Sorry, little brain part there. All right. So then down here, we're just going to take this ER, right, and then put that right there where that ER is. So this just becomes negative 36 squared divided by 1250 times cosine 25 in the I plus sine 25. And you put the 25 in the J direction. Okay, so that is what AA is. And then again, AB, we can kind of use it by inspection, or you could use that transformation over here and then just put in an angle of 0 and you get the same thing. All right, so AB is going to be equal to negative 45 squared over 1200, negative 45 squared all over 1200. In the ER direction, which is going to be equal to negative 45 squared all over 1200. All of that is going to be in the I direction. Yep, okay. Sorry, just making sure I got that right. Okay, so then now, at this point right here, we can carry out this stuff. I could say VB is seen from A is just going to be VB minus VA, so it's going to be VB minus VA, right? And now everything's in these J's line up and the I line up and whatnot. And same thing here. When I get to acceleration, it's just going to be this guy minus this guy, right? And then, we have everything in the same coordinate system, so you can do that. So I'm going to outline it right here, and then we'll call it good. So you'll go at this point, velocity of B is seen from A is going to be equal to VB, make that a little bit clearer, VB minus VA. And then acceleration of B that's seen from A is going to be acceleration of B minus acceleration of A. I'm going to call it there and just say that this, if you carry it out, right, and I'll leave the math to you here, the VB is seen from A, the magnitude of this becomes 19.6 feet per second, and the acceleration of B is seen from A. The magnitude again, put the lines on the outside, and the magnitude becomes 0.87 feet per second squared. That's your overall answer right there. Oh. Okay. Perfect. Right. And so a good exercise for you, just make sure you know how to do these things in the calculator wise, right, is you could try to make this last little step if you want to. But all I'm doing is just taking, everything has to be in the Cartesian. I'm just saying the VB is seen from A is this guy minus this guy. Right? And if you can carry that out, and then you'll get a vector with i's and j's, and you do the square root of the sum of the squares, and it gives you this. And then you do acceleration of b minus a, so you're going to go this guy minus this guy, right? Everything's in Cartesian coordinates. You're going to have i's and j's. You do the square root of the sum of the squares, and that should give you this guy down here. Okay, that is relative motion. That is kinematics of particles, right? So the next step is we're going to move on to kinetics. So next time you have class, bring in the new set of notes, and we'll go from there. So I'll post in a second here. I'm going to post this and notes from today. Lecture from today. All right, great.